All right, Joe, if that's good with you, we will get started.
Yeah.
Excellent. So, good afternoon, ladies and gentlemen. My name is Jonathan Aubertin. I am the current chair of Canada's Association, Canadian Rock Mechanics Association, CARMA. Today, we are pleased to have Dr. Joe Carvalho present as part of our webinar series. For those that are new to this series, this is something we've been trying to do with the collaboration of the CGS Rock Mechanics Division and CIM Rock Engineering Society. We try to host it every semester, so every 3 to 4 months. The webinars are recorded and are always made available on the CIM RES website and on the CARMA webpage. It's a YouTube link that you can easily access on these respective websites. Today, we have the pleasure to have, like I mentioned, Dr. Joe Carvalho present to us. Dr. Joe Carvalho is a Senior Technical Director at WSP Canada. He is a rock and fracture mechanics expert with over 40 years of experience. His work includes stress analysis for mine tunnels, foundations, underground storage, and nuclear waste disposal. He also specializes in fluid flow, hydraulic fracturing, probabilistic risk assessment, slope stability, and mine closure evaluation. Today's presentation by Dr. Carvalho is titled Artificial Crown Pillar Construction and In-Pit Tailings Disposal at Pinos Altos Complex, Mexico. As a reminder, this presentation is recorded. I would ask all participants to stay muted. We will have a period of time at the end of the presentation for Q&A. Joe, it's all yours.
Thank you, Jonathan, and thanks everybody for joining. This is work that was done quite a while back, but it's interesting work. It was probably the first of its kind. I will start by just giving you an overview of what we're trying to do, and then the chronological events that we went through to perform the design and the implementation. The case is multidisciplinary, so we'll cover these topics at a high level. There's no time to delve in detail into each one of those, and the intent is just to show the different aspects of what you might find in a pit, open pit underground interaction situation. Before I start, I want to thank Agnico Eagle Mines Ltd, and more specifically Agnico Eagle Mexico, for allowing us to do this and present this. The people from Agnico Eagle that were heavily involved in the project was Jose Cordova, Véronique Falmagne, and Michel Julien. These are their current titles in the company. Jose Cordova was the project manager in Mexico for this. Most of what's here you'll see in this reference. It's a paper that was presented at the CIM. So in 2013, Agnico Eagle operations were facing a shortage in their capacity in the tailings storage facility at Pinos Altos, and they saw the opportunity to actually put it into the pit, one of the pits. They have several pits, and they want to put it into the Oberon de Weber pit. But they always intended to go underground, so in order to do that without compromising the stability of the pit walls and the floor of the pit, which becomes the crown of the underground, and to protect the workers against unacceptable flows of tailings or water infiltration, we had to do this study. From a trade-off study that they did, the recovery of the high-grade ore at the artificial at the bottom of the pit supported the design of an artificial crown. And instead of benching down, they decided to do a narrow trench at the bottom of the pit, extract the high-grade ore, and then build a concrete artificial crown. It was also understood right from the start that they were only going to put dry stacked tailings in the pit, no slurry. So a number of scenarios were considered, including excavating a trench about 8 meters deep into the floor to extract the ore, and then replace it with a good cemented fill, providing this artificial crown. And they elected to do it with roller compacted concrete. We looked at full extraction of the stopes under the artificial crown, partial extraction under the artificial crown, and also leaving a little bit of actually rock crown below the artificial crown to help. The design of the dewatering system for the pit was also included in this, and the underground drainage. So the dewatering system was depended on the scenario that we adopted in this study. So we started by doing site investigation, followed by a risk workshop. We did some preliminary numerical analysis and 3D detailed analysis, looked at the hydrogeological characterization and the groundwater modeling, hydrology, because this is an area where it rains quite a bit, and it's in the Sierra Madre, and they have to deal with a lot of surface water draining into the pit. A little bit of geochemistry to address closure, and then the actual artificial crown design and the filter design and the pit dewatering design, followed by the placement. And of course, some instrumentation. The hydrology and surface water was limited to a review of design that they had from 9 years old. So with the investigation, this is a simplified cross-section showing the pit geology. The pit is narrow and very long and runs along the strike of the Santo Niño Fault on the hanging wall. These are photos of the west end of the pit and of the east end of the pit, showing the contact between the Buena Vista ignimbrite and the Victoria ignimbrite. It was interesting that we found these openings, which were from the turn of the other century, from some artisanal mining that existed, and they exist in other pits in the area as well. So the investigation was aimed at collecting rock mass properties and characterize the crown area, as well as obtain a better definition of the geology, like the fault and the dike on the hanging wall. We also took the opportunity at that time to install piezometers and do some hydrogeological investigation to characterize the permeability of the crown pillar and how sound it was. We also, from those cores, from those 8 boreholes, we ended up doing some rock testing. So we did uniaxial, triaxial, Brazilian tests on these samples to augment the previous testing that they had done. And you can see here, the large part of the test was done on the Buena Vista ignimbrite, which is a hanging wall rock. So with the investigation results and a little bit of preliminary analysis, I'll show later a little bit of the preliminary analysis. A risk workshop was held on site. I'm going to spend a little bit of time on the risk assessment because it was an important component of the whole project. Okay. So with the investigation results and the preliminary analysis in hand, we set up this workshop to identify the risks associated with placing the tailings in the pit while mining underground, and to determine how we could mitigate those risks with measures, and then evaluate residual risks after we put some mitigation measures in place. The system components that we considered in the analysis were the crown construction, the drainage system, the tailings placement and management itself, the underground mining, and then at the end, the instrumentation. There were a lot of stakeholders. We invited all the stakeholders to the risk workshop, from the project manager, operations director, all the way down to the paste plant manager as well, because we were going to use paste in the end, and we needed to collaborate with them for much was going on the ground, how much was available for this work. So all the stakeholders were at the table. The process. So the process is everybody sits in the room for 2 or 3 days, and we hash it out. The risk matrix shown here was used for the assessment. So you have the typical likelihood of an event occurring on the columns, and the consequence or severity of the event on the columns. The other ones on the rows. 6 categories were evaluated for for this risk workshop, and each identified risk. So we were considering safety risk, environmental risk, reputation risk to the company if things went wrong, technical risk, economic risk, and then the risk of not meeting the schedule, which is dictated by the life of the current tailings storage facility that they're running out of room in. So that's what triggered the whole process. I will go over the assessment of only one of these elements just to show how we went about it. And I'm going to look at a ground pillar. So the procedure involves going around the table, having all the stakeholders expressing their concerns and building the risk register for the element under consideration. This can be done in successive rounds until all perceived risks are exhausted. After the modes of failure were identified by all, the causes for each mode of failure are listed and the likelihood of their occurrence and the consequence are assessed, and the risk rating is attributed. So this is the one for the ground pillar. I'm just got a few sketches here. What we looked at the possibility of losing the hanging wall because we'd be mining too close to the hanging wall. So this is the condition before we have a problem. If we mine too close to the fault, we might lose the hanging wall. We might get some sloughing in, and eventually we could have a breach of that crown pillar. To control this, basically we set guidelines on the setback from the stopes to the fault, so that we get close enough that we can cause a problem. Another risk was possible washing out of hanging wall fines on a hanging wall there through the fault, and this was before. This is if we have a problem with losing fines, again we would be compromising that the concrete cap, and we could lose that as well in the same fashion. This can be controlled by protecting the area of the pit wall with the exposed fault in the dike, and I'll show you later how we did that, how we protected that area. The other one is under designing the concrete cap. See, if we don't get the right strength on the concrete cap, then this could feel some overstress from both the pit and the mining the underground stopes. And eventually, if the cap fails, we could end up with exposure of the cemented rock fill and breach of the filter and everything above. So we did some numerical analysis to try and get an estimate of the required strength for the roller compacted concrete. And then finally, construction of the cap. Poor construction control could result in a damage or not as good a crown. And in combination with blasting underground, we could end up with a compromised crown as well, and end up in the same spot. So this can be controlled with a proper quality control during construction. So just to give you an example of the things we go through, and at the end of the day, the results of the risk assessment becomes a big registry with all the risk elements: the issue, the cause, the consequence, the rating, the mitigation measure, and then after implementing all the mitigation measures, the risk is reassessed and given a new rating. And then all labels, all entries are given a label and the type of risk that they go into effect. So you end up with something like this, which for instance, in this case, a risk 2.11, it's a risk to safety, environment, reputation, and schedule. So they all have different risks. We put them on the risk matrix, and then we try to address the higher risks that we see here. So just going now into a little bit of how this was done, the analysis. The preliminary analysis were done in 2D. And what we're trying to find out here was to establish whether this rock pillar underneath the artificial RCC was required or not, and what thickness should have. So you see the top left figure is the crown pillar, the artificial crown pillar without rock. And the figure below that on the left is with a 20 meter rock pillar. And what we're looking for, and you can see here, is that without rock, you get a lot of movement up at the top of the slope and disaggregation of the rock mass. Once we help that concrete pillar with rock, then this kind of goes away and you get more stability on the walls. We tried the 10-meter pillar compared to a 20-meter, and it kind of gives you the same kind of result. And we decided that the 10-meter pillar, along with the concrete, was good enough to mitigate this issue. Looking a little bit closer, because those other figures were too small, you can see that the concrete crown here is compromised. It's yielding. It's not good enough and allows a lot of motion on the hanging wall. But leaving the pillar below the crown, this is the crown here, this is the pillar. The pillar attracts a lot of stress here, but protects the concrete crown. And you had a lot less damage in the hanging wall. And the comparison between the 10-meter and the 20-meter is kind of indicates that the 10-meter pillar is good enough. Then we went to the 3D analysis, a more detailed analysis. What you see here is a top view of the pit, and they are not taking all of the ore from the bottom of the pit. They targeted a high grade, so there's an east and a west trench that they targeted here. We didn't touch the middle, and then we wanted to see the interaction between this and excavating or mining the stopes near the ground. And I'm just going to give you a quick rundown of the 3D analysis. What you see here is the west stope and the east stopes. We didn't touch the middle, as I said. The line here is the bottom of the roller compacted concrete, and then we'll go through the sequence of excavation of the upper slopes. What you see in blue here is the hanging wall being mobilized. So that hanging wall is weak, and we already have the hanging wall at yielding at this stage. So I'll just run through a few of these in a little bit rapid motion. So taking out stopes and backfilling them, and just watching what happens to that crown. And I'll just run through the sequence here. You can see the stresses are going to start picking up a little bit near the crown. So this is as far as we went, and this is as far as they mined. You can see that on the west side, they actually mined pretty close to this, left a 10-meter pillar here. Didn't raise these up. The ore was not good enough for that. And on the east side, only two of these stopes really went all the way up and left a 10-meter pillar. The rest was left alone. And this was a combination of the ore not being worth it and safety. So from this work, the recommendations were we don't want the toe of the pit walls to be allowed to move and break through to the bottom of the pit. The RCC in the trench should have a minimum strength of 15 MPa. The rock pillar between the pit and the upper stopes is required and provides a buffer between the mining and the concrete ground. And this was to minimize disturbance of the Centennial Fault and the Oberon dike due to the underground activities. This increases the underground of operation significantly and allows time to react if something goes wrong. The pit can then be filled with rock fill or paste above the roller compacted concrete trench, and depending on the availability of materials, we designed the thing around what was available on site. A little bit on hydrology and hydrogeology. So a verification hydrological model was set up based on the following inputs. The selected design storm event used in the simulation was a 24-hour, 100-year return event with a rainfall of under 50 millimeters. This was from the NIPSL report. By the way, I was on site and we had a rainfall of about 120 millimeters in 1 day. So they do experience high rainfall. And the severe convective storm type 2 24-hour rainfall distribution was adopted for the modeling. The modeling results indicated that the peak inflow into the pit would be 14 cubic meters per second, and into the management pond, the water management pond, was 46 cubic meters per second, and this informed the design. We built a 3D groundwater model of the Oberon de Weber pipe, the site and the regional surrounds. We wanted to look at what things were doing regionally. So you calibrated that to the site data and use it as a predictive tool to support the hydrogeology component of the project. This was done with ModFlow. The key objectives were to estimate the inflow rates and water levels in the underground mining operations, predict the pumping rates required to maintain acceptable water levels in the backfill pit once they start placing the tailings, simulate groundwater recovery, and estimate flow rates and pathways for geochemical loading assessments. This is a little bit busy, but I won't belabor this. We did 4 scenarios: a pre-mine scenario to calibrate it, an active mine scenario from when the mine started until when we were doing the project, 2008 to 2014, a post-mining post-closure scenario goes from final years to post-closure from 2015 to 2115. The mine will be done in 2025, so it's actually done now. And then there's a 90-year post-closure period. And then we also looked at a storm event to provide information on the 100-year 24-hour storm event. This was the ModFlow model. As you can see, it's a regional model. This is the pit. The yellow one here is the Oberon de Weber pit. This is a larger pit they have that's also active. You can see the Oberon de Weber pit is above the underground mine here. It's not very deep. This one is much larger. So the groundwater modeling indicated that the major flows and the major streams draining into the property should be looked at to understand the groundwater and surface water systems that provide constraints to the model. Install piezometers outside of the super well. I'll come back to this super well because it's one of the key components of the design. And at several locations in the drainage blankage that was going to be constructed. And the pump, it also helped design the pump for this super well to pump water out in case it was collecting in the bottom of the pit. All of these findings and from the modeling should be integrated with the ongoing hydrological and geochemical assessments. Just a very little bit on geochemistry. We looked at acid generation potential. We collected samples. Sulfide contents were small, except one sample indicated there was, except one sample, it was indicated there was limited sulfide to generate acidity. Kinetic testings also was run, and while pH values were observed, acidic pH values were observed in the humidity cells, there was non-detectable acidity. So this was for closure, basically. We predicted a pit water quality at closure, and this kind of decided that none of these parameters were greater than the maximum guidelines when they discharged to the closed river, the river La Máquina. So again, we recommended then that a 10-meter thick rock pillar should be left in place below the artificial roller compacted concrete. The minimum strength of the concrete should be 15 MPa. The exposed fault in the hanging wall of the pit should be covered with at least 2 meters of thick layer of paste to prevent loss of fines into the hanging wall, and up to 8 meters from the bottom of the pit. And the pit dewatering should be done by pumping out of the pit by constructing this super well. We rolled out underground galleries because the ground was a very, very good quality. And the last thing we wanted to do is starting to drill holes and let the water go down into a gallery and compromise the ground. Because the ground was so good, we decided that the water should be pumped out instead of collected below. Drain and a filter should be installed at the bottom of the pit to collect the water and then deliver it to the super well for pumping. The 2-meter thick paste blanket should be constructed over the rock fill and would provide a membrane between the tailings and the rock fill below, an impervious membrane, just kind of a liner. We install piezometers outside of the super well and at several locations to keep monitoring the water pressures. And during storming events, monitor the pressures frequently to see if they're impacting the pressures in the pit. And the roller compacted concrete cap was instrumented with stress meters and extensometers. So now we've got to the building of this thing. The design, this is a cross section of the pit. Originally, if you look at the top right figure, originally there was some concern that the tailings could liquefy. So the deposition was considered in cells separated by rock fill. So what we were looking at is leaving rock fill, the blue part here, and just put the tailings in the cells to avoid problems of liquefaction. But given that this was filtered tailings, and after our analysis, we decided that we did not need to do that. So you can see here, the green part here, that's a section of the concrete. In this section is pretty thin at the bottom, and other sections is pretty square. So this is a roller compacted area that was built, artificial crown. You can see 2 meters of paste against the hanging wall. This is rock fill. So the paste was put against the hanging wall to prevent anything from going into the fault. And then a blanket of paste, cemented paste fill, to separate the upper part from the lower part. And then there was a drainage area. There was a drain and filter with a geotextile on it. And this section is still showing this rock fill over here, given that we were going to do cells, but in the end, this didn't exist. It just, the cross section would be exactly like what you see here. And then we can, add a geotextile between the drain and the filter, and then we just place the tailings. So in order to design the filters, we took the tailings, we did gradation of the tailings to see the gradation curves, and built proper filters, a transition filter and a drain. And that's how it was implemented. Now we'll look at some pictures of the implementation. So what we have here is one of the trenches being filled with this concrete, roller compacted concrete. You can see the rollers here, compacted as concrete. Obviously near the walls, it's pretty difficult to do that. So they did manual compacting on the walls here, close to the walls, to make sure there was good contact here. Once that was built, a lot of instrumentation was installed. You can see there were extensometers and stress cells. There were stress cells and extensometers. Everything got protected. These steel boxes protected the wiring and the instruments before we placed the rock fill. The rock fill crown had this kind of distribution of instrumentation. We had 4-point extensometers crossing the crown, and stress cells in a vertical hole. And we did this in 4 sections in the crown. This is a famous super well. What we did was design this piping system that was going to be installed at the base of the pit, and it was going to collect any water that might drain from the tailings through the filters, and then pumped out. You'll see that there's 3 pipes on this for redundancy, just in case one doesn't work. So in order to do this, we had to make a foundation for it. There's this concrete foundation. The first piece is bolted down to the foundation before rock fill goes around it. This is kind of the concept sketch. So 3-foot diameter pipes. The pipes are slotted through the drain to collect water, except one of them is not. There's the one that is not is slotted in the bottom, just in case some water might go past the paste and collect down in the rock fill. So a bit of redundancy on the design. So a few more pictures on the construction of this pipe. So here's the base. Here we're bolting the pipe, the first section of pipe to the base. This is about 6 meters. And you can see there's a lip on the pipe for the next section. So as they build the rock fill around this and the rock fill reaches the top of the pipe, the next section goes on before you keep going with the rock fill. It's quite a sizable pipe here. So this is the placement of the rock fill after the concrete cap is built and the first section of the pipe is installed. You can see on the right side the second section of pipe being bolted to the first section after the rock fill is placed all around it. We put around the drainage there, the slots, we put some protection, we put some drainage of filter material to prevent fines from going into the pipe. As I said, we wanted 2 meters of paste against the hanging wall. So this is cemented paste fill on the left here. This is a 2 meter distance from the wall. And as we placed the rock fill, we left that gap and we brought in the paste, cemented paste fill to block any possibility of things going into the hanging wall. And after that was done, this is the whole bottom of the pit filled with cemented paste fill, 2 meter thick layer. So this provides an impermeable membrane. And then on to placing the rest of the material. This is a bit dark because of the shadow here, but this is the paste down here. We built the drain, the filter here, and then the tailings come on top. This is a super well, so you can see that we have to build this well all the way to the top. So it's going to come in sections. It's about 90 meters high, and the sections come in as we fill it up. So another view of this. This is the drain material, just for a gauge. That pen is about 6 inches. So this is the material that we placed for drainage. You can see there's drainage material here. This is filter. There's the pipe. There's the super well, and they're already placing some tailings here. You can see there's a filter cloth placed between the tailings and the filter material. So this is the tailings placement. It's a panoramic view of the whole pit. You can see that these are dry stack tailings, so they can be placed with a dozer. They don't have to be. You can either place them with a dozer or you can put it on a conveyor belt. You don't need piping. And so once this was done, let's see how this system performed. So at the end of 2021, the high-grade western crown pillar stopes had been mined. So the underground mine under the crown was completed. Weak underground conditions in the far west end of the pit, not under the artificial crown, but on the far west of the pit, caused some delays due to progressive failure of the fault in the hanging wall. So this actually highlighted, the reason why we did all of this and the necessity of all the precautionary measures that we took when designing this. The water management, it's the only thing that is not quite performed according to plan. We had some design changes during construction, and I think we ended up with a little bit of too many fines in the bottom of that super well. So we had silting problems, and the pumps were getting plugged. So that was the one thing that if that was a learning lesson, that was it. The filter around those slots in the pipes should have been done a little bit better or constructed a little bit better. The instrumentation that's been in place since that time has provided precious insights into the RCC compacted under load. So we got good instrumentation. It's all behaving quite well. And just like I said, job done, very well done. This is a few years back where they were in the placing of the tailings. You can just see the tip of the super well over here. This is well on the way up, filling the pit. Another shot. This is another stage of it, a little bit higher. Again, super well is sitting there. You can see a truck over here, and you can see all the tailings in the pit. And then this is actually a Google shot of the pit completed. So this is fully filled now. Now there's a way out to this small creek over to this side. That's the low end of the pit. If I go back, I think you can see there's a gap here in the mountain. So you only filled up to this gap, otherwise things are going to spill out. So in closing, the project was quite a success and is operated as expected. At the time, it was probably the only in-pit tailings deposition with underground mining directly below it. I don't know if there's other mines doing that now, but I do know that there's a lot of them considering it. the advantages of doing this is that over the original tailings facility is that it's a low operating cost facility. It's very easy to manage water. It's got a lot higher stability in terms of tailings. You're not dealing with dams. It reduced the operation footprint in the area, and it provides a simpler restoration of the impacted area. So the risk assessment session held in the project early on was very, very important and very useful to improve the design and engage all the members from all the mining departments. And using this mined out openings like the Oberon de Weber pit for the tailings disposition is a good example of a sustainable mining practice. And that's why a lot of mines now are looking at the possibility to do this if you have a starter pit or you have a pit and go underground. The interesting thing is that the requirements for permits are much less stringent than if you want to build a tailings dam. And that's it for the presentation, and I'll be open to questions.
All right, thank you so much, Joe. People in the audience, please, you're welcome to ask question. I would just request that you use the raise your hand type button on your Teams app, and that will identify those who can speak next. I see this. I raise my hand, what does it do? Oh yeah, okay. Questions, or you can also use the chat there. Joe, you had a couple of questions in the chat. Maybe you want to get those?
Yeah, one of the questions is if that was the actual sequence mined. I'm not sure of that. At that point, I was not more that closely involved with the project. They didn't mine that many stopes, but I do believe that those are the stopes that ended up being mined. They didn't go beyond those. The ones on the one side, there was just 2 stopes, one at each end. The ones on the other side, there was 4 sequential ones. I do believe that went in sequence. Was there any blast vibration monitoring? Again, I'm not sure if they did that. I'm sure they have some kind of system in the mine for the underground. I don't know if they had any geophones near the surface. I'm not sure. Good question. I can find out. I can ping Veronique. She'll know.
Excellent. Any other questions? Please do use the raise hand or write the question in the chat.
And if something comes up later that you thought of, you want to ping me, you can drop me an email as well. It's okay.
Excellent. Well, I don't see any questions there, Joe, so I think we'll conclude it at that. Thank you so much for your time and for the presentation. Thank you, everybody, for attending this webinar. As mentioned, this was recorded. It will be made available online. Oh, I see somebody. No, not anymore. This was recorded. This will be made available online on the different CARMA and CIM platforms. Thank you again for your time, and I wish you a very pleasant weekend. Thank you, Joe.
Thanks, thanks, Jonathan. Thanks, everybody, for attending, and thanks for your interest. Thanks.
Thank you.
Thank you all.
Thank you so much, Joe.
Yeah, bye, Al.
Thank you. Nice.